Approximately 7,500 light-years from Earth, a star is burning with such tremendous scale that if you placed it at the center of our solar system, its surface would extend beyond the orbit of Jupiter. We thought we understood stellar size. We believed that stars, regardless of their variations, existed within comprehensible boundaries. We were catastrophically wrong about the upper limits of stellar magnitude. UY Scuti represents something almost unimaginable in cosmic architecture, a red hypergiant so enormous that our entire solar system, from the Sun to Jupiter and beyond, would fit inside its radius with room to spare. When astronomers first calculated its size using interferometry measurements from the Very Large Telescope in Chile, the numbers seemed like calculation errors. The star's radius measured approximately 740 million miles. That single measurement forced us to reconsider everything we thought we knew about the physical limits of stellar formation. To comprehend this scale requires abandoning all familiar reference points. If you could somehow hollow out UY Scuti and begin filling it with Earths, you would need approximately 5 billion of our planet to fill the volume. That number exceeds the total population of humans who have ever lived on Earth by a factor of roughly 70. Scientists at the European Southern Observatory spent 3 years verifying these measurements, checking calculations, and examining potential error sources. The conclusion remained consistent. UY Scuti ranks among the largest known stars in the observable universe. With a radius approximately 1,700 times that of our Sun, this isn't merely about astronomical records or scientific curiosities. Understanding UY Scuti's scale forces us to confront fundamental questions about stellar physics, the limits of matter accumulation in stars, and the mechanics that govern how large a star can actually become before physical laws impose absolute boundaries. Dr. Emily Levesque, an astronomer at the University of Washington specializing in massive star evolution, has noted that stars like UY Scuti exist at the absolute edge of stellar possibility. Any larger, and they would likely tear themselves apart through radiation pressure and mass loss. The discovery of hypergiants like UY Scuti has revealed that our cosmic neighborhood contains stellar objects operating under physics far more extreme than what governs our Sun. These are not stable, long-lived stars burning steadily for billions of years. They are brief, violent phenomena, stellar giants that will exist for only a few million years before exploding in supernovae that will briefly outshine entire galaxies. UY Scuti is currently in its death throes, and what we observe today represents the final chapter of stellar evolution taken to its most dramatic extreme. Throughout this exploration, we'll discover why UY Scuti challenges our understanding of stellar limits, how its size compares not just to individual planets, but to the fundamental architecture of our entire solar system, and what this star reveals about the violent, spectacular processes that govern the largest stellar objects in the universe. We'll examine why measuring such distant giants remains extraordinarily difficult, how uncertainties in distance and radius calculations affect our understanding, and why UY Scuti's exact ranking among largest known stars continues to shift as observational techniques improve. Before we begin this journey into stellar extremes, I want to ask you to do something. Subscribe to this channel and give this video a thumbs up if you're fascinated by the scale of the cosmos. And here's a question for you. If you could travel to UY Scuti and orbit at a safe distance, what do you think you would actually see? Comment below with your answer. I'll pin the most creative response. But here's what makes UY Scuti particularly fascinating from a scientific perspective. It shouldn't exist for very long. Stars this massive burn through their nuclear fuel at prodigious rates, while our Sun will shine for approximately 10 billion years. UY Scuti will exist as a hypergiant for perhaps only a few 100,000 years before its core collapses and triggers a supernova. We're witnessing this star during an extremely brief window of cosmic time, catching it in the astronomical equivalent of its final breath. What's more remarkable is that UY Scuti wasn't always this large. Like all massive stars, it began its life as a hot, blue supergiant much smaller than its current size. Though still enormous by normal stellar standards, Over millions of years, as it exhausted the hydrogen in its core and began fusing heavier elements, the star expanded to its current grotesque proportions. This expansion is inevitable for massive stars, driven by changes in internal pressure and temperature that force the outer layers to inflate to monstrous scales. The processes occurring inside UY Scuti right now involve nuclear fusion of elements far heavier than the hydrogen and helium our Sun burns. Deep in its core, silicon is fusing into iron in reactions that release tremendous energy but simultaneously doom the star. Iron fusion consumes energy rather than producing it, meaning that once a star begins creating iron in its core, the end is measured in days, not years. UY Scuti may appear stable from our distant vantage point, but it's racing toward a cataclysmic conclusion that could occur tomorrow or 1,000 years from now. This video will take you on a comprehensive journey through everything we know about UY Scuti. We'll start with how astronomers discovered and measured this stellar giant, then systematically compare its size to every major component of our solar system. We'll explore the physics that allows stars to reach such extreme dimensions, examine why UY Scuti's exact measurements remain uncertain, and investigate what its eventual death will mean for the surrounding region of space. By the end of this exploration, you'll understand not just how big UY Scuti is, but why its size represents something fundamental about the universe, a demonstration of the extreme conditions that matter can achieve under the right circumstances, and a glimpse into stellar physics operating at the absolute limits of what's physically possible. Now let's begin with the basic question: what exactly is a hypergiant star? And how did we first discover that objects like UY Scuti even exist? Cosmic giants. The story of understanding stellar giants begins not with UY Scuti, but with a fundamental revolution in how we classify stars. For centuries, astronomers observed that stars varied in brightness and color, but the physical reasons for these variations remained mysterious. The breakthrough came in the early 20th century when Ejner Hertzsprung and Henry Norris Russell independently created diagrams plotting stellar luminosity against temperature. These Hertzsprung-Russell diagrams revealed that stars occupy specific regions based on their evolutionary state, and in the upper right corner of these diagrams the region of cool, luminous stars. Astronomers found objects that defied easy explanation. Red hypergiants represent the rarest category in stellar classification. While our galaxy contains hundreds of billions of stars, fewer than 10 confirmed red hypergiants exist in the Milky Way. These objects occupy a peculiar region of stellar evolution, appearing only when massive stars, those born with at least 25 solar masses, reach late evolutionary stages. The transition to hypergiant status involves complex internal restructuring as the star exhausts hydrogen in its core and begins fusing heavier elements in successive shells on an increasingly dense iron core. UY Scuti resides in the constellation Scutum, approximately 7,500 light-years from Earth. Its location places it within the Scutum star cloud, a region rich in massive stars and stellar remnants. The star appears visually as a faint red point requiring telescopes to observe, despite its tremendous intrinsic luminosity. This apparent faintness results from two factors: the enormous distance separating us from the star, and the heavy circumstellar material surrounding UY Scuti that absorbs much of its light before it reaches Earth. The designation UY Scuti follows standard astronomical naming conventions. UY represents a variable star designation, a system that assigns letter combinations to stars showing brightness variations. Scuti indicates the constellation in which the star resides. This seemingly mundane naming convention belies the extraordinary nature of the object it identifies. When astronomers first catalogued UY Scuti in the early 20th century, they recognized it as a variable star but had no conception of its true scale. The tools to measure stellar radii accurately at such distances didn't exist until decades later. What makes hypergiant stars like UY Scuti physically possible? The answer involves understanding the balance between gravity trying to compress a star and pressure from nuclear fusion trying to expand it. In normal stars like our Sun, this equilibrium remains stable for billions of years. But in massive stars, the rate of fusion increases dramatically with stellar mass. A star 25 times more massive than the Sun produces roughly 80,000 times more energy. This tremendous energy output creates intense radiation pressure that can actually overcome gravity and blow material away from the star's surface. Red hypergiants form when massive stars have exhausted hydrogen fusion in their cores and transition to fusing helium and heavier elements. This transition causes the star's outer envelope to expand dramatically while the surface temperature decreases, giving the star its characteristic red color. The physics governing this expansion involves complex interactions between radiation, convection currents moving material through the star's outer layers, and changes in opacity that affect how easily energy can escape from the stellar interior. UY Scuti's classification as a red hypergiant places it in the same category as other extreme stellar objects like UY Canis Majoris, Westerlin 1-26, and RW Cephei. These stars share several characteristics: extreme luminosity, cool surface temperatures around 3000 to 4000 Kelvin, massive mass loss through stellar winds, and variability in brightness. The variability occurs because the outer envelopes of these stars are only loosely bound by gravity. Pulsations and convection cells the size of Earth's orbit move through the stellar atmosphere, creating irregular changes in the star's apparent size and brightness. The discovery that stars could reach sizes measured in hundreds of millions of miles came gradually. Early estimates of stellar radii relied on indirect methods measuring a star's luminosity and temperature, then calculating the radius needed to produce that luminosity at that temperature. These calculations has suggested that some red supergiants might be extraordinarily large, but confirmation required direct measurement techniques. The development of interferometry in the late 20th century finally provided astronomers with tools capable of resolving the disks of distant giant stars. Interferometry works by combining light from multiple telescopes to create the resolving power of a much larger telescope. The Very Large Telescope Interferometer in Chile uses for 8.2-meter telescopes that can work together to achieve resolution equivalent to a telescope over 100 meters in diameter. When astronomers pointed this instrument at UY Scuti and similar hypergiants, they measured angular diameters, the apparent size of the star as seen from Earth, combined with distance estimates. These angular measurements yielded actual physical radii that confirmed the extreme sizes predicted by theoretical models. UY Scuti's measurements revealed a radius of approximately 740 million miles, though this number carries significant uncertainty. The star's radius varies over time as it pulsates, and the heavy circumstellar material surrounding it makes determining where the surface actually lies a matter of some interpretation. Different wavelengths of light penetrate to different depths in the stellar atmosphere, so measurements at infrared wavelengths give slightly different radii than measurements at visible wavelengths. Despite these complications, all measurement techniques agree on one fundamental conclusion: UY Scuti ranks among the largest stars ever measured. The implications of this size are profound. A star this large has a mean density lower than the air you're breathing right now. If you could somehow transport a cubic meter of material from UY Scuti's outer envelope to Earth's surface, it would weigh only a few grams. The star achieves its tremendous mass not through density but through sheer volume, the same principle that makes a hot air balloon float despite containing massive amounts of air. UY Scuti's outer layers are so diffuse that by some definitions, they barely qualify as matter at all, existing in a state between gas and the vacuum of space. Understanding UY Scuti's place among stellar giants requires recognizing that size and mass don't correlate directly in evolved massive stars. While UY Scuti has a radius over 1,000 times that of the Sun, its mass likely measures only 25 to 30 solar masses. It began life with more mass, but has been shedding material through stellar winds for millions of years. The star loses mass at a rate of approximately 1 Earth mass every few thousand years, a rate that sounds slow but accumulates to significant mass loss over the star's lifetime. This mass loss creates the complex circumstellar environment surrounding UY Scuti. The star exists within a shell of its own discarded material, gas and dust blown away by radiation pressure and stellar winds. This material absorbs much of the star's light and re-radiates it at infrared wavelengths, contributing to the difficulty of observing and measuring the star accurately. Future observations with instruments like the James Webb Space Telescope may penetrate this dusty envelope more effectively. potentially refining our understanding of UY Scuti's true size and structure. The existence of stars like UY Scuti tells us something fundamental about stellar evolution. The path from birth to death for massive stars involves temporary phases of extreme expansion. Every star with sufficient initial mass will eventually pass through a red giant or supergiant phase, and the most massive stars achieve hypergiant status. UY Scuti represents the future of all massive stars, a glimpse into the dramatic finale awaiting objects that begin their lives with vastly more mass than our Sun will ever possess. Discovery dawned. The systematic observation of UY Scuti began in the early 20th century. Though the star had doubtless been catalogued in earlier sky surveys without recognition of its extraordinary nature. The first astronomers to note UY Scuti observed its variability. Its brightness changes over irregular periods measured in months and years. This variability placed it among thousands of other variable stars, objects that merit attention but weren't initially recognized as particularly special. The true revelation of UY Scuti's nature required technological developments that wouldn't arrive for decades after its initial cataloging. Variable stars have fascinated astronomers since ancient times, but understanding what causes stellar variability required knowledge of stellar structure that emerged only in the 20th century. Some stars vary because they're actually binary systems where one star periodically eclipses the other. Other stars vary intrinsically, their brightness changing due to physical processes occurring in or on the star itself. Pulsating variables like Cepheids expand and contract regularly, while eruptive variables undergo sudden outbursts. UY Scuti belongs to a less regular category, semi-regular variables that show brightness changes without strict periodicity. The recognition that UY Scuti might be extraordinarily large came from spectroscopic studies conducted in the mid-20th century. When astronomers dispersed the star's light into a spectrum, they found absorption lines indicating a cool surface temperature combined with features suggesting extremely low surface gravity. Low surface gravity implies either low mass or enormous size, and given the star's considerable luminosity, enormous size became the more plausible explanation. These early spectroscopic clues hinted that UY Scuti might rank among the largest stars in the galaxy, but confirming this required direct size measurements. The breakthrough in measuring UY Scuti's size came with interferometric observations conducted using the Very Large Telescope Interferometer in Chile in the early 21st century. A team led by astronomers from the European Southern Observatory targeted several red supergiant and hypergiant candidates, including UY Scuti, with the goal of directly measuring their angular diameters. The observations took place over multiple nights to account for atmospheric distortions and instrumental variations. When the data was finally processed, the results indicated an angular diameter of approximately 5 milliseconds, an angle so small that it's equivalent to viewing a golf ball from a distance of roughly 7,000 miles. Converting angular diameter to actual physical size requires accurate distance measurements, and herein lies one of the major sources of uncertainty in UY Scuti's radius calculation. The star's distance was initially estimated at 9,000 light-years based on spectroscopic parallax, a technique that estimates distance by comparing a star's spectral characteristics to similar stars with known distances. Later studies using different methods, including analysis of the surrounding interstellar extinction and comparisons with stellar evolution models, SUGGSTD distances ranging from 7,000 to 10,000 light-years. A difference of 3,000 light-years translates to a 40% variation in calculated radius, illustrating why UY Scuti's exact size remains somewhat uncertain. Despite these uncertainties, the interferometric measurements definitively established UY Scuti as one of the largest known stars. The published radius of approximately 740 million miles, or roughly 1,700 solar radii, placed it at or near the top of stellar size rankings. This measurement sparked considerable public interest, with science communicators and astronomy enthusiasts seizing on UY Scuti as an example of cosmic extremes. For several years, UY Scuti was widely cited as the largest known star in the universe, though subsequent observations and ray analyses have shown that several other hypergiant candidates might rival or exceed its size. The challenge of accurately measuring hypergiant radii extends beyond simple distance uncertainty. These stars don't have sharply defined surfaces like planets do. Instead, their outer atmospheres gradually thin into surrounding space, with density decreasing over distances that can span millions of miles. Where exactly does the star end and space begin? Different measurement techniques effectively probe different depths into this extended atmosphere, yielding radius measurements that vary depending on the wavelength of light used and the specific properties being measured. Modern stellar models suggest that UY Scuti's radius varies by perhaps 10 to 15% over timescales of months to years due to pulsations in its outer envelope. The star breathes, expanding and contracting in irregular patterns driven by complex interactions between radiation pressure, convection currents, and gravitational forces. When we cite a single radius value for UY Scuti, we're really describing an average or typical size, acknowledging that the actual radius at any given moment might be somewhat larger or smaller. The measurement of UY Scuti's properties represents a triumph of modern observational astronomy, to resolve and measure an object just 5 milliseconds across, located thousands of light-years away. Required instruments operating at the absolute limit of what's technically possible. The Very Large Telescope Interferometer achieves this by combining light from telescopes separated by over 100 meters. Using laser guide stars to compensate for atmospheric turbulence, and employing sophisticated data processing algorithms to extract meaningful measurements from incredibly faint signals. Complementary observations at infrared wavelengths have provided additional insights into UY Scuti's structure. The star is surrounded by warm dust that radiates primarily in infrared, created from material blown off the stellar surface by radiation pressure and stellar winds. This circumstellar envelope extends far beyond the star's photosphere, the visible surface, and contains complex molecules and dust grains formed from elements synthesized in the star's interior. Observations by infrared telescopes like Spitzer and Herschel have mapped this extended envelope, revealing structures that provide clues about the star's mass loss history and current evolutionary state. The discovery and characterization of UY Scuti also benefited from advances in stellar atmosphere modeling. Theoretical astrophysicists can now create detailed computer models of how radiation propagates through the extended, cool atmospheres of red hypergiants. These models predict what spectrum the star should produce at different wavelengths, what its angular diameter should be when observed with interferometry, and how its properties should vary with pulsation phase. Comparing these model predictions to actual observations helps astronomers refine both the models and their interpretation of the observational data. One particularly illuminating aspect of UY Scuti's study involves comparing it to similar hypergiants at different evolutionary stages or with different initial masses. By studying a sample of such stars, astronomers can piece together the evolutionary path that massive stars follow and understand how properties like radius, luminosity, and mass loss rate change over time. UY Scuti appears to be in a relatively late evolutionary stage, having already shed significant mass and expanded to near its maximum possible size. Comparing it to slightly younger or less evolved hypergiants helps astronomers understand what fate likely awaits this stellar giant in the coming millennia. The scientific papers describing UY Scuti's properties typically include extensive discussions of measurement uncertainties and systematic errors. The quoted radius of approximately 1,700 solar radii might be accurate to within 10 or 20%. Or the uncertainty could be larger if unrecognized systematic errors affect the measurements. Astronomy at this level involves careful statistical analysis, Monte Carlo simulations to propagate uncertainties, and honest acknowledgement of what we know confidently versus what remains ambiguous. Recent observations have attempted to refine UY Scuti's distance using advanced techniques including analysis of the interstellar absorption lines in its spectrum. By studying how light from UY Scuti is affected by intervening dust and gas, astronomers can estimate how much material lies between us and the star, which provides constraints on its distance. These studies generally support a distance in the range of 7,000 to 8,000 light-years, somewhat closer than earlier estimates. If confirmed, this would mean UY Scuti is slightly smaller than the maximum values sometimes quoted, though still unquestionably among the largest stars known. The story of UY Scuti's discovery and measurement illustrates how modern astronomy progresses, patient observation accumulating over decades. Technological advances enabling previously impossible measurements. Theoretical models providing context for interpreting data, and ongoing refinement as new techniques and instruments come online. What began as an entry in a catalog of variable stars has become one of the most extensively studied examples of stellar extremes, a benchmark against which other hypergiant candidates are compared, and a window into the physics of matter under conditions that push the boundaries of stellar possibility. Measurement mystery. Measuring the radius of a star located thousands of light-years from Earth presents challenges that extend far beyond simply pointing a telescope and taking a picture. And like planets in our solar system, which sub-10 measurable angular sizes and show visible disks even in modest telescopes, stars are so distant that even the largest remain point sources in conventional telescopes. The angular diameter of UY Scuti as seen from Earth measures approximately 5 milliseconds, an angle roughly equivalent to observing a quarter from a distance of 500 miles. Resolving such minute angular scales requires specialized techniques that push observational astronomy to its limits. Interferometry, the primary technique used to measure UY Scuti's size, works by exploiting the wave nature of light. When light from a distant star reaches Earth, it arrives as plane waves with specific phase relationships between different parts of the wavefront. By collecting this light at 2 or more telescopes separated by a baseline distance, then combining the light and examining the interference pattern, astronomers can extract information about the star's angular size. The longer the baseline between telescopes, the finer the angular resolution that can be achieved. The Very Large Telescope Interferometer uses baselines up to 200 meters, providing angular resolution better than 2 milliseconds under ideal conditions. The practical execution of interferometric observations involves numerous challenges. Earth's atmosphere constantly distorts incoming light through turbulence, making the interference patterns fluctuate rapidly. Adaptive optics systems partially compensate by using deformable mirrors that adjust thousands of times per second to counteract atmospheric distortion. Even with these corrections, observations must be carefully timed to occur when atmospheric conditions are optimal, typically during stable weather with minimal wind and temperature gradients. A single reliable measurement might require combining data from multiple nights of observation. Beyond atmospheric effects, accurately measuring UY Scuti's angular diameter requires accounting for the star's extended atmosphere. Red hypergiants don't have sharp photospheric boundaries like the Sun. Instead, their atmospheres extend gradually into space, with density and temperature changing over distances comparable to the radius of Earth's orbit. Different wavelengths of light probe different depths in this extended atmosphere. Measurements at visible wavelengths effectively measure the radius at optical depth unity, the depth from which photons can escape without further scattering. Infrared measurements probe deeper layers where temperatures are higher and conditions differ. This wavelength-dependent radius means that the radius of UY Scuti isn't a single, precisely defined quantity. The distance to UY Scuti represents another major source of measurement uncertainty. Trigonometric parallax, the most direct distance measurement technique, involves observing how a star's position shifts relative to background stars as Earth orbits the Sun. For nearby stars within a few hundred light-years, this technique provides highly accurate distances. But UY Scuti's distance of roughly 7,500 light-years produces a parallax angle far too small to measure accurately even with space-based instruments like Gaia. Instead, astronomers must rely on indirect distance estimation methods, each carrying substantial uncertainties. Spectroscopic parallax estimates distance by determining a star's absolute luminosity from its spectral characteristics, then comparing this to its apparent brightness to calculate distance. For UY Scuti, this involves modeling the star's atmosphere to determine its effective temperature and luminosity, then using stellar evolution theory to check consistency with models of hypergiant stars. Different assumptions about the star's mass, metallicity, and evolutionary state yield different distance estimates. Published distance values for UY Scuti range from 7,000 to nearly 10,000 light-years, representing uncertainty of over 40%. This distance uncertainty directly propagates to radius uncertainty. If UY Scuti lies at 7,000 light-years, its measured angular diameter corresponds to a radius of approximately 1,400 solar radii. If it lies at 9,000 light-years, the same angular measurement implies a radius of roughly 1,800 solar radii. The star's ranking among largest known stars depends critically on which distance estimate proves correct, and current observational techniques cannot definitively resolve this ambiguity. Additional complications arise from UY Scuti's intrinsic variability. The star pulsates irregularly, with its brightness changing by roughly 1 magnitude over periods of months to years. These brightness variations reflect actual physical changes in the star's radius and temperature. During bright phases, the star has contracted and heated slightly. During faint phases, it has expanded and cooled. Interferometric measurements taken at different phases would therefore yield different radius values. Published measurements typically represent single-epoch observations, offering a snapshot of the star's size at one particular moment rather than a time-averaged mean radius. The circumstellar envelope surrounding UY Scuti adds yet another layer of measurement complexity. The star has been shedding mass through stellar winds for millions of years, creating a shell of gas and dust extending far beyond the photosphere. This material absorbs and scatters light from the star, affecting measurements in wavelength-dependent ways. At visible wavelengths, the dust absorption is severe, dimming the star by several magnitudes. Infrared observations penetrate the dust more effectively, but even at these wavelengths, some absorption occurs. Determining the star's intrinsic properties requires carefully modeling this circumstellar extinction and correcting observational data accordingly. Modern attempts to refine UY Scuti's measurements employ multiple complementary techniques. High-resolution spectroscopy reveals absorption lines formed at different depths in the stellar atmosphere, providing information about temperature and density structure. Photometric monitoring tracks brightness variations over time, yielding constraints on pulsation periods and amplitudes. Infrared observations map the temperature and structure of the circumstellar dust shell. Each technique provides independent constraints, and combining all available data through sophisticated modeling yields more robust estimates than any single measurement alone. Comparison with stellar evolution models offers an additional consistency check. Theoretical models predict how stars of different initial masses evolve, including predictions for radius, luminosity, surface temperature, and mass loss rates at different evolutionary stages by comparing UY Scuti's observed properties. To model predictions, astronomers can assess which evolutionary tracks best match the observations. These comparisons generally suggest that UY Scuti began life as a star with 25 to 30 solar masses and has now reached late hypergiant evolution, consistent with its observed properties. However, uncertainties in the models, particularly regarding mass loss rates and convection efficiency, prevent using this approach to determine the radius with high precision. The ongoing debate about UY Scuti's exact size and ranking among largest stars reflects healthy scientific practice. Initial measurements suggested it might be the largest known star, but subsequent observations of other hypergiant candidates and refinements to UY Scuti's own measurements have revealed a more nuanced picture. Stars like Stephenson 218, Woji 64, and Westerlund 1-26 have comparable or potentially larger radii, though all of these measurements carry similar uncertainties. Rather than definitively ranking these objects, astronomers now recognize a group of roughly 10 hypergiant stars with radii around 1,000 to 2,000 solar radii, all pushing the upper limits of stellar size. This situation illustrates a broader principle in astronomy. Measurements of extreme objects at the boundaries of observational capability inherently carry large uncertainties. As techniques improve and new instruments come online, these uncertainties will gradually decrease. The James Webb Space Telescope's infrared capabilities may enable better characterization of UY Scuti's circumstellar environment. Future extremely large telescopes with mirror diameters of 30 to 40 meters will achieve even finer angular resolution. Improved parallax measurements from future astrometry missions might narrow distance uncertainties. Each advance will refine our understanding of UY Scuti's true size. For now, the most honest statement about UY Scuti's radius acknowledges both what we know confidently and what remains uncertain. The star is definitely among the largest known, with a radius exceeding 1,000 solar radii and likely falling between 1,400 and 1,800 solar radii. Its exact ranking among largest stars depends on measurement details and may never be determined with absolute certainty, given the inherent challenges of measuring such objects. What matters scientifically is not the ranking itself but what UY Scuti reveals about stellar physics at extreme scales, how stars can grow so large, what processes limit their maximum size, and how these stellar giants eventually end their lives. The measurement challenges surrounding UY Scuti underscore an important aspect of cutting-edge astronomy. The objects that push our understanding forward, the most distant galaxies, the smallest exoplanets, the largest stars, inevitably exist at the boundaries of what current technology can measure. Progress requires not just better instruments but also sophisticated analysis techniques, careful error estimation, and honest communication about uncertainties. UY Scuti's story demonstrates how science advances. Tentative initial measurements spark interest, subsequent observations refine understanding, competing explanations are tested against data, and gradually a more complete picture emerges even if some questions remain incompletely resolved. Planetary perspective. To grasp UY Scuti's scale requires comparing it systematically to familiar objects, beginning with the planets of our solar system. Consider Mercury, the innermost planet orbiting at an average distance of 36 million miles from the Sun. Mercury's orbital radius is less than 1/20th of UY Scuti's radius. If you placed UY Scuti at the center of our solar system, Mercury's entire orbit would lie deep within the star's interior, with the planet itself vaporized instantly by temperatures exceeding thousands of degrees even in the star's relatively cool outer layer. Rupees. Venus orbits at 67 million miles from the Sun, yet this distance still falls well within UY Scuti's radius. The second planet would suffer the same fate as Mercury, consumed by the hypergiant's extended atmosphere. At these depths within UY Scuti, though temperatures are far cooler than the star's core, they still reach several thousand degrees, more than sufficient to reduce solid matter to plasma. The region where Venus orbits the Sun would, inside UY Scuti, exist as a diffuse gas with density lower than the best vacuum achievable in Earth laboratories, yet still hot enough to glow faintly if you could somehow view it from outside. Earth orbits 93 million miles from the Sun, at a distance we call 1 astronomical unit. This familiar distance, the space that sunlight traverses in 8 minutes, represents barely 1/8 of UY Scuti's radius. Our planet, with all its complexity, its atmosphere and oceans and teeming life, would be engulfed by the hypergiant if it replaced our Sun. The region of UY Scuti corresponding to Earth's orbital distance still maintains temperatures of perhaps 2,000 degrees. Incompatible with solid planets but similar to conditions found in the photospheres of cooler red dwarf stars. Mars, orbiting at 140 million miles, extends the comparison further. The red planet's distance from the Sun equals roughly 1/5 of UY Scuti's radius. At this depth within the hypergiant, conditions begin transitioning from the star's middle atmosphere to its outer envelope. Temperatures decline somewhat, but density increases as you move inward. The gas pressure at this depth, though still extraordinarily low by terrestrial standards, would be sufficient to crush any spacecraft attempting to penetrate it. The radiation environment would be intense, with ultraviolet and X-ray photons produced in the star's hotter inner regions gradually working their way outward through millions of miles of stellar atmosphere. The asteroid belt, occupying the region between Mars and Jupiter, with most asteroids orbiting between 200 million and 300 million miles from the Sun, would lie entirely within UY Scuti. Millions of rocky bodies, the shattered remnants of planetesimals that never coalesced into a planet, would find themselves inside the hypergiant's extended atmosphere. Ceres, the largest asteroid and the only dwarf planet in the inner solar system, orbits at approximately 250 million miles, still only 1/3 of UY Scuti's radius. The entire population of main belt asteroids, containing perhaps 2 million objects larger than 1 kilometer, would be consumed by the star. Jupiter, the solar system's largest planet, orbits at 480 million miles from the Sun. This distance approaches but does not exceed UY Scuti's radius. The hypergiant surface, defined as the photosphere where optical depth reaches unity, extends to approximately 740 million miles, meaning Jupiter's orbit would lie in UY Scuti's outer atmosphere, perhaps 2/3 of the way from the star's center to its visible edge. At this location within the hypergiant, temperatures have cooled to perhaps 1000 degrees, and density has decreased to levels barely distinguishable from interstellar space. Yet even this tenuous material would exert drag on Jupiter, gradually spiraling the planet inward to destruction over timescales that, while long, would be finite. The implications of these comparisons extend beyond mere numerical relationships. They reveal something profound about the structure of space in our solar system. We tend to think of the Sun as the dominant feature, with planets orbiting in the surrounding emptiness. This perspective is valid for our particular star, which has a radius of only 430 to 1,000 miles, tiny compared to planetary orbital distances. But UY Scuti demonstrates that stars can expand to scales where the distinction between star and planetary system becomes blurred. The hypergiant's atmosphere extends across distances that, in our solar system, encompass multiple planetary orbits. Consider what it would mean for a planet to orbit at a distance where it would be engulfed by UY Scuti's atmosphere. The planet would experience drag forces from the surrounding gas, yes, but the material would be so diffuse that it might take thousands or millions of years for the orbit to decay significantly. During that time, strange phenomena would occur. The planet's atmosphere, if it had one, would be slowly stripped away by the hypergiant stellar wind. The planet's surface would be heated not by a distant point source, but by being literally immersed in glowing gas. Tidal forces from the star might become significant, possibly even disrupting the planet if it ventured too close. None of Jupiter's moons would survive if that planet orbited inside UY Scuti's atmosphere. Io, Europa, Ganymede, and Callisto, the Galilean satellites that have fascinated astronomers since their discovery 4 centuries ago, would be vaporized by the ambient temperature and radiation environment. The Moon system that makes Jupiter so interesting as an object of scientific study would be impossible in such an environment. This illustrates how stellar properties constrain what's possible in planetary systems. Habitable planets require stars stable and compact enough to provide the right conditions at appropriate distances. Saturn orbits at 886 million miles from the Sun, comfortably beyond even UY Scuti's extended atmosphere. This distance exceeds the hypergiant's radius by roughly 20%, meaning Saturn would survive, at least initially, if UY Scuti replaced our Sun. However, the planet would orbit not in the empty space it enjoys in our actual solar system, but in the extended stellar wind and radiation field of the hypergiant. The famous rings would likely be disrupted by radiation pressure and particle impacts from the stellar wind. The planet itself would be heated to temperatures far higher than it experiences now, possibly triggering atmospheric changes and preventing the formation of the beautiful banded structure we observe today. Uranus and Neptune, orbiting at 1,700,000,000 and 2,800,000,000 miles respectively, would be well clear of UY Scuti's physical radius. These ice giants would experience the hypergiant as an intensely luminous but distant object. However, even at these distances, UY Scuti's tremendous luminosity, perhaps 400,000 times that of our Sun, would raise temperatures significantly. Uranus would be heated to perhaps twice its current temperature, while Neptune would experience similar warming. The delicate balance of heat and chemistry that determines these planets' atmospheric properties would be fundamentally altered. The dwarf planets of the outer solar system provide further scale references. Pluto, orbiting at an average distance of 3,600,000,000 miles, resides nearly 5 times farther from the Sun than UY Scuti's radius. Other trans-Neptunian objects like Eris, Makemake, and Haumea orbit at even greater distances, well beyond any direct influence from the hypergiant's atmosphere. Yet even these remote objects would be affected by UY Scuti's presence through its intense radiation field. The frozen ices that compose much of these worlds' surfaces would sublime it more rapidly, creating temporary atmospheres and altering surface chemistry. These planetary comparisons serve a purpose beyond mere wonder. They ground UY Scuti's abstract radius in familiar contexts, transforming an incomprehensible number into something you can grasp by reference to known distances. When you consider that Earth orbits 93 million miles from the Sun, and UY Scuti's radius exceeds 700 million miles, you're not just comparing numbers, you're recognizing that the star's size fundamentally reimagines what we mean by stellar architecture. The hypergiant isn't just a bigger version of the Sun, it's a qualitatively different type of object, operating under physical conditions so extreme that they challenge our solar system-based intuition about how stars work. Orbital engulfment. The comparison between UY Scuti and planetary orbits raises a fascinating question. What would happen if such a star actually replaced our Sun? The transformation would be catastrophic and immediate, but understanding the specifics requires considering both the hypergiant's size and its other physical properties. UY Scuti doesn't just occupy more space than the Sun, it radiates approximately 400,000 times more energy, generates powerful stellar winds, and creates a radiation environment utterly unlike what exists in our solar system. Mercury's orbit, at 36 million miles, would place this planet deep within UY Scuti's middle atmosphere, where temperatures still reach thousands of degrees. The planet itself would vaporize almost instantly, its rocky material dissociating into a plasma of individual atoms. But the destruction wouldn't end there. The vaporized material would add to the stellar atmosphere, mixing with the hydrogen and helium that dominates UY Scuti's composition. Over time, this material would be carried upward by convection currents or blown away in the stellar wind, eventually dispersing into interstellar space. No trace of Mercury would survive beyond a slight enrichment in heavy elements in a small region of the hypergiant's outer layers. Venus, at 67 million miles, would meet a similar fate. The second planet's thick carbon dioxide atmosphere would provide no protection against the hypergiant's heat. At the temperatures existing within UY Scuti at this radius, no molecule can remain intact. Even atomic bonds between carbon and oxygen would be broken, reducing the planet's atmosphere to individual atoms in a plasma state. The planet's solid surface would vaporize, transforming approximately 5 times Earth's surface area of rock into diffuse gas mixed through a volume larger than the inner solar system. The sulfuric acid clouds that shroud Venus in our actual solar system would be impossible. Complex molecules cannot exist at temperatures exceeding several thousand degrees. Earth, at 93 million miles, poses more interesting questions because this distance lies in UY Scuti's outer atmosphere, where conditions, while still extreme by any reasonable standard, are less immediately catastrophic. The temperature at Earth's orbital distance within the hypergiant might be around 2,000 degrees, well above the melting point of rock, but cool enough that atoms can begin forming simple molecules. Earth's vaporization would proceed more gradually than Mercury's or Venus's, perhaps taking hours or days rather than seconds. The oceans would boil away first, followed by the atmosphere, then the rocky crust and mantle. Eventually, the planet would be reduced to a cloud of gas mixing into the stellar atmosphere. But something remarkable might occur during this destruction. As Earth vaporized, its more volatile elements would form a temporary enrichment in UY Scuti's atmosphere. A brief increase in elements like oxygen, silicon, and iron at a specific radius within the star. This material would gradually disperse, but for a time, you might be able to detect its presence spectroscopically as unusual absorption lines in the hypergiant spectrum. Earth's death would leave a fleeting chemical signature, a ghost of the planet's composition temporarily imprinted on its destroyer's atmosphere. Mars, at 140 million miles, would experience somewhat less severe conditions but still face inevitable destruction. The red planet's thin atmosphere would be stripped away first. Blown off by the hypergiant's stellar wind, the surface would then heat to incandescence, glowing red then white as temperatures climbed. The planet's famous iron oxide dust would decompose, releasing oxygen atoms that would mix with the surrounding stellar material. The Veils Marineris, Olympus Mons, and all the other geological features that make Mars scientifically fascinating would melt and vaporize, transforming from solid rock to glowing gas over timescales measured in years. The asteroid belt presents an interesting scenario, and like planets, asteroids are not bound together by significant self-gravity. They're simply rocks following individual orbits around the Sun. When embedded in UY Scuti's atmosphere, each asteroid would experience drag forces from the surrounding gas. This drag would cause orbital decay, making the asteroids gradually spiral inward, but the time scale for this process depends on the asteroid's size and the local gas density. Smaller asteroids might spiral in and vaporize within thousands of years, while larger objects like Ceres could potentially survive for much longer, slowly losing mass through surface vaporization while their orbits decayed. Jupiter's situation at 480 million miles from the Sun becomes complex because this distance puts the planet in UY Scuti's outermost atmosphere. The gas giant would orbit within a region where stellar material transitions from being gravitationally bound to the star to escaping as stellar wind. Jupiter would experience continuous drag from the surrounding medium, causing its orbit to decay over time. But it would also experience heating from being immersed in gas at perhaps 1,000 degrees. This heating would cause Jupiter's atmosphere to expand, potentially making the planet grow larger even as it slowly spiraled inward toward denser regions of the hypergiant. The decay timescale for Jupiter's orbit would depend sensitively on the local gas density, which is poorly constrained by current observations. If the density at Jupiter's orbital distance within UY Scuti is similar to typical stellar wind densities, the orbital decay time might be millions of years, long enough that Jupiter could complete many orbits before spiraling in. During this time, the planet would shed its own atmosphere gradually, the outer layers being stripped away by stellar wind while the core potentially survived. Eventually, perhaps tens of millions of years after being embedded in the hypergiant's atmosphere, even Jupiter's core would spiral inward enough to be destroyed. Saturn, at 886 million miles, would orbit just beyond UY Scuti's visible photosphere, in a region where stellar material has already expanded to densities approaching interstellar space. The ring planet would experience intense heating from the hypergiant's radiation. UY Scuti's luminosity is approximately 400,000 times the Sun's, meaning that at Saturn's distance, the received radiation would be about 60 times more intense than what Earth receives from our Sun. This would heat Saturn to temperatures far above what it experiences in our actual solar system, possibly triggering atmospheric convection patterns very different from what we observe today. Saturn's rings would likely be destroyed relatively quickly by radiation pressure from the hypergiant. The countless ice particles that make up the rings would be heated by the intense radiation, causing them to sublime it. Water vapor released from the ice would form a temporary atmosphere around the planet, but this would gradually be lost to space or dissociated by radiation. Over thousands to millions of years, the magnificent ring system would dissipate, leaving Saturn as a ringless gas giant orbiting an aging stellar monster. Uranus and Neptune, orbiting at approximately 2 billion and 3 billion miles respectively, would be far enough from UY Scuti to survive in recognizable form. These ice giants would not be engulfed by the star's atmosphere, nor would they experience the immediate vaporization that would destroy the inner planets. However, they would still be profoundly affected by the hypergiant's presence. The intense radiation would heat these planets to several times their current temperature, potentially altering the balance of chemistry in their atmospheres. The methane clouds that give these planets their blue color might be replaced by different cloud systems reflecting changed atmospheric conditions. The outer solar system's small bodies, the dwarf planets, Kuiper belt objects, and comets of the Oort cloud would represent the only components of the solar system to survive essentially intact. These objects orbit at such great distances that even UY Scuti's tremendous luminosity would affect them only mildly. They would be warmed somewhat, causing increased sublimation of surface ices, but the basic structure and composition of these objects would remain recognizable. In a perverse sense, the outer reaches of the solar system would become a refuge, the only region where solid matter could stably exist. This thought experiment reveals how profoundly stellar properties shape what's possible in planetary systems. Our solar system's architecture: rocky planets close to the Sun, gas giants at intermediate distances, ice worlds in the outer system exists precisely because the Sun is a stable, compact star with a radius of only 432,000 miles. If the Sun were as large as UY Scuti, no planets could exist at their current locations. The entire familiar structure of the solar system depends on having a star that maintains a small, well-defined photosphere orbited by planets in empty space. Hypergiant stars make planetary systems impossible, at least in any form we would recognize. Surface journey. Imagining a journey across UY Scuti's surface requires first confronting a conceptual challenge. The star doesn't have a surface in the way planets do. Earth's surface is a well-defined boundary between solid rock and atmospheric gas. You can stand on it, measure its altitude, and locate yourself precisely. UY Scuti possesses no such boundary. Its visible surface, the photosphere, is simply the depth at which the stellar material becomes opaque enough that photons can no longer escape without scattering. This photosphere exists not as a physical boundary but as a gradual transition from transparent to opaque occurring over distances of thousands of miles. Nevertheless, if we define UY Scuti's surface as the photosphere and imagine traveling along this spherical shell, the distances involved become staggering. The star's circumference, calculated from its radius of approximately 740 million miles, equals roughly 4,600,000,000 miles. To travel this distance at the speed of a commercial jet aircraft, about 500 miles per hour, would require over 1,000 years of continuous flight, at the speed of light, the fastest speed possible in the universe. Circumnavigating UY Scuti would take approximately 6 hours and 45 minutes. Consider what you would see during such a journey. UY Scuti's photosphere has a temperature around 3,500 Kelvin, giving it a deep red color. This is cooler than an incandescent light bulb filament, though still far hotter than anything you would experience on Earth. The surface would glow with a dull red luminosity, similar to heating metal until it's red hot but before it reaches yellow or white heat. This relatively low surface temperature, cool by stellar standards, results directly from the star's enormous size. UY Scuti's internal nuclear reactions generate tremendous energy. But this energy must radiate away through a surface area so vast that each square meter radiates relatively little energy compared to hotter, more compact stars. The view outward from UY Scuti's surface would be remarkable. The stellar atmosphere extends gradually into space, with no clear boundary separating star from space. You would be surrounded by a diffuse gas with density low enough to qualify as an excellent vacuum by Earth laboratory standards, yet still dense enough to absorb and scatter light. The sky would appear strange, not black as it appears from Earth, but filled with a faint red glow from the stellar atmosphere extending above and around you. Stars would be visible, but dimmed and reddened by the intervening gas. The familiar constellations would appear subtly distorted as light from distant stars passed through UY Scuti's extended atmosphere. Looking inward toward the star's center would offer no view at all. The stellar material, though diffuse, would be opaque over distances of just a few hundred miles. You could not see to the star's core, nor even to depths much greater than the local photosphere thickness. The view would resemble being inside a glowing red fog that extends uniformly in all directions, with no visible features to orient yourself except perhaps the gradual change in brightness as you look toward or away from the stellar interior. UY Scuti's surface would exhibit large-scale convection cells, regions where hot gas rises from below, cools slightly, and sinks back down. These convection patterns occur in the outer layers of all cool giant stars. But the scale on UY Scuti would be extraordinary. Individual convection cells might span millions of miles, larger than the entire Sun. These cells would create temperature variations across the stellar surface, with some regions perhaps 100 degrees hotter than others. These temperature differences would be visible as slightly brighter and dimmer patches on the star's surface, similar to the granulation pattern visible on the Sun but occurring at vastly larger scales. The granulation cells would be in constant motion. Hot gas rising from the stellar interior would reach the photosphere, radiate energy into space, cool, and begin sinking. This creates a circulation pattern with upwelling regions appearing brighter due to higher temperature, and downwelling regions appearing darker and cooler. The velocity of these convection currents might be on the order of 10 to 20 miles per second, far faster than any weather system on Earth, but slow by astronomical standards. If you could somehow maintain position on UY Scuti's surface, you would see the granulation pattern slowly shifting and evolving, with hot cells rising and cool materials sinking in a perpetual cycle driven by the temperature gradient between the star's hot interior and cool outer atmosphere. UY Scuti also exhibits larger-scale pulsations that cause its entire surface to expand and contract. These pulsations occur over irregular periods measured in hundreds to thousands of days. During expansion phases, the photosphere moves outward by millions of miles. The surface temperature decreases slightly, and the star's total luminosity increases somewhat as the larger surface area more than compensates for the lower temperature. During contraction phases, the process reverses. The amplitude of these pulsations might be 10 to 15% of the star's radius, variations of over 100 million miles in the location of the photosphere. The mechanism driving these pulsations involves complex interactions between radiation pressure, gas pressure, and gravitational forces in the star's outer envelope. In some layers, increased compression causes increased opacity, which traps radiation and builds pressure that drives expansion. This expansion then causes cooling and decreased opacity, allowing radiation to escape and reducing the pressure, which allows contraction. The cycle repeats, creating oscillations that can persist for extended periods. These pulsations represent one way that massive evolved stars become unstable, a precursor to the more dramatic instabilities that will eventually destroy the star. Imagine being present on UY Scuti's surface during one of these pulsation cycles. Over a period of months, you would see the horizon gradually receding as the photosphere expanded outward. The surface area would increase, the local temperature would decrease slightly, and the density of the surrounding gas would diminish. Then, over the following months, the process would reverse. The horizon would gradually approach as the star contracted, temperature would increase, and the surrounding gas would become marginally denser. These changes would occur slowly enough that day-to-day differences would be imperceptible, but over timescales of months, the transformations would be dramatic. The magnetic field environment on UY Scuti remains poorly understood but is likely very different from the Sun's well-studied magnetic structure. The Sun's magnetic field is generated by dynamo action in the convection zone and emerges through the photosphere to create sunspots, prominences, and coronal structures. UY Scuti's convection zone extends through most of the star's outer envelope, potentially generating magnetic fields through similar dynamo processes. However, the extreme scale and low density of the hypergiant's outer layers might make magnetic field generation less efficient. If magnetic fields do exist, they would be stretched and distorted by the convection currents and stellar winds, creating complex topologies very different from the relatively organized field structures seen on the Sun. Stellar winds on UY Scuti would be continuously blowing material away from the surface. The star loses mass at a rate estimated at approximately 1/10,000th of a solar mass per year, roughly 1 Earth mass every few thousand years. This sounds slow, but over the star's lifetime, it adds up to significant mass loss. The wind would be felt as a constant outward pressure, with gas at the photosphere being accelerated outward to escape velocity. This process is driven primarily by radiation pressure on dust grains that condense in the cool outer atmosphere. Photons from the star's interior push on these dust particles, which collide with gas atoms and drag them along, creating an outward flow. The dust that forms in UY Scuti's outer atmosphere consists of various compounds formed from elements synthesized in the star's interior and dredged up to the surface by convection. These might include silicate minerals similar to those found in rocky planets, carbon-rich compounds like graphite, and various metal oxides. The dust grains start forming at temperatures around 1000 to 1500 Kelvin, where molecules can become stable and begin condensing into solid particles. As these particles form, they become effective absorbers of radiation, allowing stellar photons to push them outward. The dust is then carried away in the stellar wind, eventually spreading into interstellar space where it might someday contribute to the formation of new stars and planetary systems. If you could somehow stand on UY Scuti's surface, obviously impossible given the lack of a solid surface and the hostile conditions, you would experience gravity far weaker than on Earth, despite the star's enormous mass of roughly 25 solar masses. The gravity at the photosphere would be only about 1% of Earth's surface gravity. This occurs because gravity decreases with the square of distance from a mass center, and UY Scuti's radius is so enormous that the photosphere lies extremely far from the star's center. The weak surface gravity explains why the star can maintain such an extended, tenuous atmosphere. There's insufficient gravity to compress the material into a more compact configuration. The weak gravity also explains UY Scuti's instability. In a stable star like the Sun, gravity firmly holds the outer layers in place against radiation pressure. In UY Scuti, the balance is much more precarious. Radiation pressure, convection currents, and pulsations can all cause material to move significant distances because gravity provides only weak restraining force. This makes the star highly susceptible to mass loss and contributes to the irregular variability seen in its brightness. The star exists in a regime where the usual stable balance between gravity and pressure that characterizes normal stars has broken down, replaced by a barely controlled instability that will eventually lead to the star's destruction. Walking around UY Scuti's surface, if such a thing were possible, would reveal a world almost incomprehensible in its scale and strangeness. Every feature would be measured in millions of miles. Temperatures would melt any known material, and the environment would be simultaneously nearly a perfect vacuum yet dense enough to be opaque over modest distances. This is a realm where human intuition fails completely, where the rules governing matter and energy operate in regimes far removed from anything accessible to direct experience. And yet, understanding these conditions teaches us about the extreme states that matter can achieve under the right circumstances, about the physics that operates when stars push against the absolute limits of size and luminosity. Stellar evolution. UY Scuti's enormous size is not a permanent condition but a temporary phase in stellar evolution, a brief interlude in the life story of a massive star. To understand how stars reach hypergiant dimensions requires tracing the evolutionary path from birth to the current state, understanding the nuclear processes occurring in the stellar interior, and recognizing that the size we observe today represents only one moment in a transformation that will end catastrophically. Stars form from gravitational collapse of giant molecular clouds, regions of space where gas and dust accumulate to sufficient density that gravity can overcome thermal pressure and pull material together. In regions where particularly dense clumps exist, contraction continues until the central temperature rises high enough to ignite nuclear fusion. For stars that will eventually become hypergiants, this requires an initial mass of at least 25 solar masses. Such massive stars are relatively rare. For every star born with enough mass to eventually become a hypergiant, roughly 1,000 lower mass stars form simultaneously. When massive stars first begin nuclear fusion, they appear as hot, luminous blue stars O-type or B-type supergiants with surface temperatures exceeding 20,000 Kelvin and radii perhaps 20 or 50 times that of the Sun. At this stage, the star burns hydrogen in its core through the CNO cycle, a set of nuclear reactions that uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. The CNO cycle is far more temperature sensitive than the proton-proton chain that powers lower mass stars like the Sun, meaning that massive stars generate energy at prodigious rates. A star with 25 solar masses might radiate 100,000 times more energy than the Sun. This extraordinary energy output has consequences. The massive star exhausts its core hydrogen much faster than less massive stars do. While the Sun will burn hydrogen for approximately 10 billion years, a 25 solar mass star will deplete its core hydrogen in just 5 to 7 million years. This rapid consumption of nuclear fuel drives the evolutionary sequence that will eventually produce a hypergiant. Once core hydrogen is exhausted, the star must reorganize its interior structure to continue generating energy. The exhaustion of core hydrogen causes the star's core to contract and heat while the outer envelope expands dramatically. This transition transforms the star from a compact blue supergiant into a larger, cooler red supergiant. The expansion occurs because the star now generates energy in a shell surrounding the inert helium core rather than in the core itself. This shell burning phase produces different pressure and temperature structures that cause the outer layers to inflate. The star's radius might increase by a factor of 10 to 50 during this transition, while the surface temperature decreases from 20,000 Kelvin to perhaps 5,000 Kelvin. As the core continues contracting and heating, it eventually reaches temperatures sufficient to ignite helium fusion approximately 100 million Kelvin. Helium fusion produces carbon and oxygen through the triple alpha process, a reaction requiring 3 helium nuclei to collide nearly simultaneously. This phase provides a new source of energy that temporarily stabilizes the star, but the respite is brief. Helium burning in massive stars lasts only a few 100,000 to 1 million years before the core helium is exhausted. The pattern repeats with progressively heavier elements. After helium exhaustion, the core contracts further, heating until carbon fusion ignites at temperatures around 600 million Kelvin. Carbon fusion produces neon, magnesium, and sodium. This phase lasts perhaps 1,000 years. Next comes neon fusion, then oxygen fusion, then silicon fusion, each occurring at higher temperatures, each lasting shorter periods. Silicon fusion produces iron, and here the sequence terminates because iron fusion consumes energy rather than producing it. During these successive burning phases, the star's outer envelope continues expanding to ever larger radii. The star transitions from red supergiant to red hypergiant as the radius grows from hundreds of solar radii to more than 1,000 solar radii. This expansion is driven by the increasing luminosity of the star as progressively more energetic nuclear reactions occur in nested shells around the core. The total energy output increases dramatically, pushing the outer envelope to enormous dimensions. The weak surface gravity of such large stars cannot hold the outer layers tightly, allowing them to expand to extraordinary scales. UY Scuti currently sits somewhere in this evolutionary sequence, likely in the late stages of helium or carbon burning. The star has already expanded to its maximum size, or close to it, as the increasingly energetic fusion processes in its interior push the envelope outward against the weak gravitational restraint. The exact evolutionary state is difficult to determine precisely because stellar models for such extreme objects carry significant uncertainties, but the star's properties, its high luminosity, cool temperature, and enormous size all indicate late evolutionary stages. The star is also losing mass rapidly through stellar winds, at an estimated mass loss rate of approximately 1/10,000th of a solar mass per year. UY Scuti is shedding its outer envelope into space. This mass loss is driven by radiation pressure on dust grains forming in the cool outer atmosphere, as discussed earlier. The lost material forms a circumstellar envelope that extends far beyond the photosphere, carrying away not just mass but also angular momentum and energy over the star's life as a hypergiant. It may lose 10 to 15 solar masses of material, substantially reducing its total mass. This mass loss has profound implications for the star's future. The final fate of a massive star depends critically on how much mass remains when the core finally collapses. Stars retaining more than about 25 solar masses at the time of core collapse will likely form black holes directly, with the entire star disappearing into the event horizon without producing a visible supernova. Stars with somewhat less mass will explode as supernovae, ejecting their outer layers while the core collapses to form either a black hole or neutron star. UY Scuti's extensive mass loss suggests it will fall into the latter category, producing a supernova that will briefly become one of the brightest objects in the sky visible from Earth. The timescale for UY Scuti's remaining life is very uncertain but likely measures in hundreds of thousands of years at most, and potentially as little as a few thousand years. The star has already consumed most of its nuclear fuel and exists in the final phases before core collapse. When the iron core grows to approximately 1.4 solar masses, the Chandrasekhar limit, it will no longer be supported by electron degeneracy pressure. The core will collapse catastrophically in less than 1 second, releasing gravitational binding energy equivalent to about 10% of the core's rest mass. This energy will drive the outer layers of the star into space at velocities reaching 30,000 miles per second. The supernova that will mark UY Scuti's death will be visible from Earth as an extremely bright transient, possibly reaching apparent magnitude of -10 or brighter, bright enough to be visible during daytime and to cast shadows at night. The event will be observed by astronomers around the world, producing a wealth of data about supernova physics and massive star evolution. The expanding supernova remnant will enrich the interstellar medium with heavy elements synthesized in the star's interior, contributing to the raw materials from which future generations of stars and planets will form. After the initial explosion, the supernova remnant will continue expanding for thousands of years, gradually dissipating into the surrounding interstellar medium. The core, compressed to nuclear densities during the collapse, will likely form a neutron star city-sized object with mass around 1.5 solar masses and a radius of only 10 miles. Alternatively, if the core retains sufficient mass during collapse, it might form a stellar mass black hole with a radius of just a few miles. Either outcome represents an almost incomprehensible compression of matter, the final transformation of a star that began life spanning hundreds of millions of miles across. The inevitability of UY Scuti's eventual destruction illustrates a fundamental principle of stellar evolution. Massive stars live fast and die young. The very nuclear reactions that make them so luminous and spectacular also doom them to brief lives and violent deaths. We observe UY Scuti during a fleeting interval of cosmic time, witnessing a state that will soon on astronomical timescales transition to something entirely different. The star serves as a reminder that even the largest, most impressive objects in the universe are temporary. Their existence bounded by the finite supply of nuclear fuel and the inexorable progression of physical processes that will eventually transform them beyond recognition. Mass paradox. One of the most counterintuitive aspects of UY Scuti involves the relationship between its size and mass. Despite being over 1,000 times larger than the Sun, UY Scuti contains only about 25 to 30 solar masses, far less than might be expected for a star of such dimensions. This creates a paradox. How can a star so enormous contain so little mass? The answer reveals fundamental insights into stellar structure and the different roles that mass and radius play in determining a star's properties. The key to resolving this apparent paradox lies in understanding that stellar radius and mass are not directly proportional, especially for evolved stars. When stars are on the main sequence burning hydrogen in their cores, there exists a relatively straightforward relationship between mass and radius. More massive main sequence stars have larger radii, with radius scaling roughly as mass to the power of 0.7. But this relationship breaks down completely when stars evolve off the main sequence and enter red giant or hypergiant phases. The expansion that occurs during these evolutionary stages is driven by changes in the star's internal structure rather than by increased mass. Consider UY Scuti's average density. With a radius of approximately 740 million miles and a mass of roughly 25 solar masses, the star's mean density is extraordinarily low, approximately 1/10,000,000th that of the Sun, or about 1/100,000th the density of Earth's atmosphere at sea level. This is far more tenuous than any gas you encounter in everyday experience, approaching the density of the best vacuum achievable in terrestrial laboratories. The star is so diffuse that in a real sense, it barely qualifies as a material object at all. This extreme low density results from the star's evolutionary history. UY Scuti began life as a compact, massive star with a radius perhaps 20 times that of the Sun, over millions of years. As it exhausted hydrogen in its core and transitioned through successive phases of helium, carbon, and heavier element burning, the outer envelope expanded dramatically. This expansion was not accompanied by mass increase. In fact, the star has been losing mass through stellar winds throughout its evolution. The expansion occurred because the increasing luminosity from more energetic fusion reactions in the core and surrounding shells pushed the outer layers outward against the weak gravitational restraint. The physics governing this expansion involves radiation pressure and the structure of stellar atmospheres, as nuclear reactions in the stellar interior produce increasingly high-energy photons. These photons exert outward pressure on the overlying material in massive, evolved stars. This radiation pressure becomes comparable to or exceeds the inward pull of gravity, especially in the outer layers. Additionally, the opacity of the stellar material, its ability to absorb and scatter light, increases as density decreases and temperature drops, making the outer atmosphere very effective at capturing radiation and converting it to outward pressure. These factors combine to push the outer envelope to enormous radii despite the star's relatively modest mass. Comparing UY Scuti to other stellar objects illustrates how unusual its mass-to-radius ratio is. The Sun has a mass of 1 solar mass and a radius of 432,000 miles, giving it a mean density about 1/4 that of Earth. White dwarfs typically have masses around 0.6 solar masses but radii comparable to Earth about 4,000 miles, giving them densities around 1 million times that of the Sun. At the opposite extreme, UY Scuti has 25 times the Sun's mass but a radius 1,700 times larger, giving it a density roughly 1 million times lower than the Sun. Stars span an enormous range of density, from white dwarfs denser than any matter found in terrestrial experience to hypergiants more tenuous than any laboratory vacuum. The low density has profound implications for UY Scuti's stability. With such weak gravitational binding, the outer layers are barely held to the star at all. The escape velocity at UY Scuti's photosphere is only about 30 to 40 miles per second, far lower than the several hundred miles per second typical for compact stars. This low escape velocity means that material in the outer atmosphere can be relatively easily accelerated to speeds sufficient to escape the star entirely. Stellar winds, pulsations, or other disturbances can eject material into space, contributing to the ongoing mass loss that characterizes hypergiant evolution. The weak surface gravity also affects the scale height of the atmosphere, the distance over which atmospheric density decreases by a factor of approximately 0.7 in Earth's atmosphere. The scale height is about 5 miles above this altitude. Density has dropped to 37% of its sea level value. On UY Scuti, the scale height measures millions of miles. This means the atmosphere transitions extremely gradually from relatively dense inner regions to the tenuous outer envelope. There's no sharp boundary analogous to Earth's Kármán line where atmosphere transitions to space instead. Density simply decreases smoothly over distances comparable to planetary orbital radii in our solar system. Despite its low mass compared to its size, UY Scuti still represents one of the most massive stars known. Very few stars form with masses exceeding 25 solar masses, making objects like UY Scuti rare even before considering the additional rarity of the brief hypergiant phase. The mass distribution of stars at birth. The initial mass function is heavily weighted toward low-mass stars. For every star born with 25 solar masses, there are roughly 10,000 stars born with masses similar to the Sun, and millions of stars born with masses below half a solar mass. Massive stars are cosmic rarities, and hypergiants are the rarest massive stars of all. The relationship between UY Scuti's current mass and its initial mass illustrates another important aspect of stellar evolution. The star almost certainly formed with significantly more mass than it possesses today, perhaps -15 to 40 solar masses. Throughout its evolution, mass loss through stellar winds has gradually reduced this mass to the current value. This mass loss accelerated dramatically once the star entered the red supergiant and hypergiant phases, as the cool, extended atmosphere became conducive to dust formation, and radiation pressure on dust grains drove powerful stellar winds. The mass loss has altered UY Scuti's evolutionary trajectory. A star of 35 solar masses evolving without mass loss would follow a different path than a star that loses 15 solar masses over its lifetime. The mass loss affects the star's luminosity, its internal structure, the timescales for successive nuclear burning phases, and ultimately the nature of its final collapse and explosion. Modeling stellar evolution for massive stars requires accounting for these mass loss processes, which remain incompletely understood and represent a significant source of uncertainty in predictions about the future evolution of stars like UY Scuti. Another consequence of the low mass-to-radius ratio involves the star's rotational properties. Stars conserve angular momentum as they evolve, meaning that expansion should cause rotation to slow, the same principle that causes a spinning ice skater to slow down when extending their arms. UY Scuti's enormous expansion from its initial radius to its current size should have caused its rotation period to increase from perhaps 1 day to several years. Observations suggest that hypergiant stars like UY Scuti do indeed rotate very slowly, with periods that might be measured in months or years. This slow rotation has implications for the star's magnetic field generation and for the angular momentum content of its stellar wind. The mass paradox also manifests in gravitational effects. Despite its enormous size, UY Scuti's gravitational influence at large distances is determined only by its mass, not its radius. At distances beyond the star's photosphere, gravitational effects depend solely on the 25 solar masses, meaning that if you could replace the Sun with UY Scuti while somehow avoiding the immediate effects of the star's heat and luminosity, the orbits of planets beyond Jupiter would not change significantly. Gravity from a spherical mass distribution appears to objects outside that distribution, as though all the mass were concentrated at a point at the center. UY Scuti's enormous size is irrelevant to its gravitational effects on distant objects. This principle has interesting implications for any planets that might somehow exist around a hypergiant. The planet's orbits would be determined by the star's mass, not its size. A planet orbiting at a distance great enough to avoid being engulfed by the star's atmosphere would experience gravitational forces similar to what it would feel orbiting a much more compact star of the same mass. The main differences would come from effects other than simple gravitational attraction: the intense radiation, the stellar wind, and tidal forces arising from the star's enormous spatial extent. Understanding the mass-radius relationship for stars like UY Scuti requires abandoning intuitions based on everyday experience with solid objects. For familiar objects like planets or human-scale things, density remains relatively constant, so mass scales with volume and thus with radius cubed. For stars, density varies wildly with evolutionary state, and the relationship between mass and radius becomes complicated and dependent on internal structure. UY Scuti exemplifies the extreme end of this variation, a star whose size exceeds by far what its mass alone would suggest. Inflated to enormous proportions by internal energy generation that pushes the envelope outward against weak gravitational restraint. The result is an object barely held together by its own gravity, existing in a precarious balance that will inevitably be disrupted when the star's nuclear fuel finally runs out. UY Scuti is not a static object but rather a dynamic, changing star whose properties vary measurably over time. This variability manifests in brightness changes that can exceed 1 magnitude, corresponding to intensity variations of more than a factor of 2. These changes occur regularly over timescales ranging from hundreds to thousands of days, making UY Scuti a semi-regular variable star. Understanding this variability provides insights into the physical processes occurring in the star's outer layers and the fundamental instabilities that affect hypergiant stars in their final evolutionary stages. The variability was first noticed during the early 20th century observations that led to UY Scuti's initial cataloging. Astronomers conducting sky surveys noticed that the star's brightness changed measurably between observations separated by months or years. This variability earned it the variable star designation UY in the Scutum constellation, placing it among thousands of other stars showing brightness variations. Initially, astronomers didn't know what caused the variations. But as understanding of stellar structure advanced, it became clear that the changes reflected real physical processes occurring in the star rather than observational artifacts. The primary mechanism driving UY Scuti's variability involves pulsations in the star's outer envelope. These pulsations are not regular oscillations like the beating of a drum but rather complex, partially chaotic movements driven by the interaction between radiation pressure, convection currents, and gravitational forces. The star's outer layers expand and contract in patterns that don't repeat precisely from cycle to cycle. During expansion phases, the photospheric radius increases by tens of millions of miles, the surface temperature decreases slightly, and the star's total luminosity increases as the enlarged surface area more than compensates for the lower temperature. During contraction phases, these changes reverse. The driving mechanism for these pulsations involves opacity variations in certain layers of the stellar atmosphere. In regions where particular ionization states of elements dominate, the opacity, the efficiency with which material absorbs and scatters light, increases sharply when the material is compressed. This creates a valve-like mechanism. Compression increases opacity, which traps radiation and builds pressure that drives expansion. Expansion decreases opacity, allowing radiation to escape, and reducing pressure, which permits contraction. This cycle repeats, creating oscillations that can persist for extended periods. However, UY Scuti's pulsations are not purely periodic. Observations show that while the star exhibits typical pulsation periods of several hundred to 1,000 days, individual cycles vary in amplitude and duration. This quasi-periodic behavior suggests that multiple pulsation modes are operating simultaneously, interfering with each other to create the irregular variability pattern observed. Theoretical models of hypergiant pulsations predict precisely this sort of complex behavior, with different radial and non-radial oscillation modes excited simultaneously and beating against each other to produce the observed irregularity. The amplitude of UY Scuti's brightness variations about 1 magnitude corresponds to changes in radius of roughly 10 to 15%. When the star is at maximum size, its radius might be approximately 800 million miles, at minimum size, perhaps 700 million miles. These 100 million mile variations represent significant physical changes, but they occur slowly enough that the star never reaches dynamically unstable conditions. The pulsations are ultimately driven by the fundamental instability of the star's structure, the precarious balance between radiation pressure pushing outward and weak gravity pulling inward. But they don't directly threaten to tear the star apart. Rather, they represent the star's attempt to find equilibrium under conditions where true equilibrium is impossible. Temperature variations accompany the radius changes. When UY Scuti is smallest contracted, its surface temperature reaches its maximum of perhaps 3,700 Kelvin. When expanded, the temperature drops to perhaps 3,300 Kelvin. These temperature changes alter the star's spectral appearance. At maximum temperature, the star appears somewhat brighter and shifts slightly towards shorter wavelengths. At minimum temperature, it appears fainter and redder. These changes can be tracked through photometric observations in different wavelength bands, with measurements at visible wavelengths showing larger variations than infrared measurements due to the wavelength dependence of the star's emission. The variability also affects the star's spectrum in more subtle ways. Absorption lines formed in the stellar atmosphere shift and change strength as the atmosphere expands and contracts. During expansion, the outer atmospheric layers move outward, causing spectral lines to show blue-shifted absorption components. During contraction, the reverse occurs. The strength of various spectral lines changes as temperature and density in the line-forming regions vary. Detailed spectroscopic observations can thus provide information about the pulsation amplitude and velocity distribution in the stellar atmosphere. Convection in UY Scuti's outer envelope adds another layer of complexity to the variability. Giant convection cells rising and falling through the star's atmosphere create local temperature and brightness variations that contribute to the observed light curve in addition to the global pulsations. These convection cells are enormous, potentially spanning millions of miles and containing more mass than Jupiter. As these cells rise to the photosphere, they create temporarily bright regions. As they sink back into the interior, they create darker regions. The statistical average of many such cells produces the smooth light curves observed, but individual cells might create localized variations detectable in high-resolution interferometric observations. The stellar wind emanating from UY Scuti also varies with the pulsation cycle. During expansion phases, when the photosphere is largest and coolest, the conditions become particularly favorable for dust formation. More dust grains form during these phases, increasing the opacity and making the stellar wind more efficient at coupling to radiation pressure. This causes the mass loss rate to vary cyclically, with more mass loss during expansion phases than during contraction. Over many pulsation cycles, this pattern contributes to the overall mass loss from the star, with perhaps half of the total mass loss occurring during the expansion phases, even though these phases occupy less than half of the total time.